Hello everyone. In this session, I'm going to talk about the support vector regression mechanism. So here we would be using support vector machines, the concepts of the support vector machines exclusively for regression purpose. When I say regression purpose, the response variable for me is not a categorical variable. The response variable is actually a quantitative or a numerical variable. So I am trying to do a numerical prediction. So my objective is I'm trying to do a numerical prediction by using a set of attributes, and it is in these cases I can use the concept of regression. But here we will try to do the regression using the concepts of support vector machine. So the relationship between my response variable and a set of attributes, right? So the response variable is y, set of attributes are different x's. Support vectors are typically built to showcase the relationship between these set of variables, and that is how the overall model will be built, and that model can very well be used for future prediction of this y values. So that is what is the typical process that goes in here. As a part of this, we would be looking at three major algorithms. Of course, again, we can talk about a few more, just like on the case of just like the way we have looked at the regression models or classification models from the kernlab package or even E1071 package. Just like the way we have looked at the classification models from these packages, we can also look at the regression models more or less from these set of packages itself, because your EPS regression and new regression, both of them are coming from E1071 package, whereas bound constraint EPS regression, EPS is epsilon. So epsilon regression is actually coming from your kernlab package. So I would be using these two packages with again the same set of functions. For these two we are using a function SVM, which we have used for classification purposes as well, and here we are going to use KSVM again, which we have used during the classification purpose. So I really don't need to go in detail and explain each of these functions, because we have already discussed them in detail in our session on classification. So let's try to see, by taking a data set, how we can typically build a model, build a regression model using the support vector machines on the training data, and how we can really do the testing of the same, and how we can really assess the accuracy or the goodness of fit of that particular model. So just getting in, starting off with EPS regression, which is the epsilon regression. I would be using it with the 1071 E1071 package and the SVM function, something that is very much needed. So first let me load the data. Here I am taking a insurance related data, right? I have loaded it from my folder to this particular location. So let me just have a quick look at this particular data set. So I am looking at DIM of insurance saying 1338 rows and 7 columns are there. Let me look at the head of this insurance to see what actually it contains. So there is something called insurance charges, which is what I would like to model. So this would be my response variable. I would like to check whether the insurance charges are by any chance dependent on the age of the person, the sex of the person, the BMI associated with the person, number of children the person has, because it's like a group insurance kind of a plan, or depends on whether the person is a smoker or not and to which region he or she belongs to. So I really want to build a model. So here my response variable is a quantitative variable. So regression is a kind of necessity in this case. We can very well build different kinds of models, right? But now we are looking at how we can use support vector machines for doing this concept of regression, right? And let me quickly look at seeing the basic checkup of the data, if there are some kind of abnormalities and all. But before we do that, let me just load our package again, E1071 package. Okay, I have loaded the package. A quick look at the SVM function from this package, though we have done a lot of understanding of it when we did the classification part. But a quick check says here I need to give, so here it can be used to carry out general regression as well as classification. I can do both of them. Now you could see it is asking for a formula which we will provide because we know the response variable and we also know the attributes with which we can use this. Then the data is something that I can very much provide. I need to provide the kernels again. So I can use any one of these 4 kernels as we have used earlier: the linear, the polynomial, the radial, or the sigmoid. We can use any of these kernel functions and various other things that I can give as input to it. By default, the scaling is true, and which means the size, we don't need to really bother about the size. The size adjustment is automatically taken care of. The thing is type. Type, I have to set it explicitly. Here in the types, we have already looked at C classification, which is for a classification problem. New classification also is for a classification problem. One classification is for novelty detection. Even this we have done. Now we are looking at EPS regression. The next topic in the same session we will look at new regression, which means these are just by changing the type, we are dealing with 2 different algorithms for the same purpose, right? And we can very well look at these 4 different kinds of kernel functions out here. And by default, all the costs, epsilon is set as a default value. The epsilon is typically set at 0.1, which is the parameter which can very well be played around with. Gamma, again, if we are going with a radial, so for each of the kernels we have different parameter values that need to be specified, but at the same time the system is taking some default set of values, and it's our responsibility to really play around with different sets of values for the parameters and see which parameters are more apt for this data set. But as I am discussing things out here, I am more and more focusing on the default implementation itself, because after that it's a matter of you looping the stuff, making sure that all combinations of the parameters are taken care of before you coming out with the best possible model for the data set that you have taken, right? So this is what is the model that we are working with. So just by changing the type from EPS hyphen regression to new hyphen regression, we would be taking care of 2 different models out here. Cost also by default it is set as 1, but we can very well change the cost parameter as well. You could see the cost of constraint violation. So by default it is set as 1, you can very well change it to any other number as well. So that is how we have to use it on this data. So we'll go ahead and use it, fair enough. But before that, let me just see if there are some kind of abnormalities as a part of the data, right? I should try to see the summary of this data to see if there are some kind of abnormalities in the data. So I'm looking at a summary of insurance. Age is looking like a numerical variable 18 to 64. Sex is a categorical variable. There are 662 females and 676 males, more or less equally distributed. BMI is ranging from almost 15.96 to 53.13 numerical. Children ranging from 0 to 5. Smokers, almost 1000 out of the total set of people, they are smokers. Out of the 1338, only 26, sorry, non-smokers, and only 274 of them are smokers. When it comes to the region, I think more or less everyone is from the same region. I mean, equally distributed into the 4 regions. Charges is looking like pretty much spread out, right? Minimum is 1122 to maximum of 63,770. So sometimes if required, I can very well get into the transformations itself in case I see that there are too many abnormalities, right? If I want, I can very well make the charges as log charges, and I can use those log charges as a kind of response variable rather than using the charges. So it's up to me to really see what is the distribution that is associated with the response variable, and based on that, if I want to do some kind of transformations on the response variables or any of the attributes, I can very well do those activities as well. So right now my focus is I'll take the things as it is for executing the model, but wherever required I'm giving you the pointers so that you can improvise your model. So SVM, Y is my response variable, but here this response variable should be a numerical variable, right? It should be a continuous variable. Then dot saying all other attributes are contributing to it. Then data is something that I have to specify. What is the data frame on which this SVM model needs to be built? The kernel function I have to specify. So in the E1071, as we have been discussing, 4 kernel functions are supported: the linear kernel, the polynomial kernel, the sigmoid kernel, and we also have the support of radial basis kernel. So these are the 4 kernel functions that are typically supported. The cost, talking about the scope of error, the type, which is mentioning the EPS regression here, we will have the new regression for the next one. And all the other things, they are taken as default, but if required, you can very well change them as well. Change the default values to some other value. Overall, playing around so that you will get the best possible output on the process. Now coming to the steps of execution, initially load your E1071 package, done. Get the necessary data, done. Do a preliminary inspection. I don't see any NAs in my data. So summary wise also, when I have seen, I could see that only in the response variable, which is the charges, I see that there is a lot of abnormality in the data, lot of outliers that could be possible, right? Even if required, you can do the you can load the psych package and do the description of the data as well to confirm which of them are very highly skewed. So I can very well go with a describe. I can go with a describe of insurance to see for each of them. I can ignore the characteristic based data, but look at the BMI or look at the age. Skewness is very much around 0. I don't need to bother too much about the skewness, but look at the BMI. Even the BMI has a skewness of around 0.28, looks more or less normally distributed. But look at the charges, it looks slightly highly skewed, right? Positively skewed. So that is an indicator that there might be a couple of outliers that could be present in the data on the higher side, and that is what could force me to look at some kind of a transformation, like a logarithmic transformation on that data, so that the response variable comes more or less into the normal range. But again, these are all the different kinds of options that I can very well try. And finally, the objective for me is to get the best possible output, the best possible model, which is having a much higher level of accuracy when I am doing it on my testing data, so that I can very well roll it out into the production process. Now, taking it as it is as an assumption, now the next thing is I have to split the data into the training and the testing. So I will set a seed first of all. I'll set some number 1000. Now I have to pick up, there are 1338 rows. So let me take 1338 into 0.7, giving me 937. So I will take 70%, which is 937 random values from 1 to 1338. For that I am using the sample function, where between 1 to 1338 I want the system to pick up 937 values randomly without any kind of replacement, without any kind of duplication. So this is what are the set of values. 937 values are randomly picked up between 1 to 1338 without any kind of duplication. Now what I want to do is I'll split my data into training data, which is a subset of insurance, which will contain the rows which have come as a part of the train and all the columns. Whereas my testing data will contain those rows which did not come as a part of the train. So that's where I'm taking minus train and all columns. So my data is broken down into a training data as well as the testing data. So even this is there in place for me right now. Now estimate the support vector machine using the default settings. Now I can very well go ahead with the default settings. Only thing is I will set the type as EPS regression, and probably the kernels I can go with all the 4 kernels. So I'll call it as fit linear, fit EPS linear is what, let me take, epsilon regression, linear kernel. So we will use the SVM function, where my dependent variable is charges tilde dot. All others I am taking them as attributes. Data for me is coming from insurance, and now I should not take insurance, I should take the training data. So I'll take train data. I'm building the model only with the train data. I'll test it on the test data. The type I'm setting it as EPS hyphen regression. The type I am setting as EPS hyphen regression, and kernel I will set it as linear kernel. That's it. So I am putting a regression out here. Same lines I can very well fit all the 4. So kernel I will set it as polynomial. For a polynomial default here, all the parameters I am taking them by default, remember that, but I can very well change all the parameters. Similarly, I can set a radial kernel with its own default parameters. So we need to understand, for each kernel there are a set of parameters which are by default, right? So we have the option to change them. Similarly, I can go with a sigmoid kernel. So these are the 4 kernels that are supported as a part of this SVM. Again, as a user of all these models, the way I look at it is, you just take each of these different options on your data set, see once you build your model to what extent your objective is getting met in terms of making accurate predictions on your testing data. That's the easiest way rather than a theoretical way of looking at whether for this data this particular model would be a fit or not. Quickly, if I want to see, let me just check out each of these models. Right, fit EPS linear, I'll simply type it, which says number of support vectors are 383. But more than simply typing it, I suggest that you can try the summary function. Slightly, it may give you the same. So whatever, even if you are typing the value or even if you are typing the summary, both of them are giving you the same kind of a result, right? So the number of support vectors in this case is coming out to 383, and we will try to do the testing of it by doing a prediction, right? But if you are doing a plot of this model, so this model is not getting plotted, so we don't have a plot function for this model, leave it. Now looking at the fit EPS poly, here it is taking the default gamma. Gamma is being taken as 0.111 because you have by default it takes 1 by the number of columns. So based on that the gamma value has been chosen as this. The number of support vectors in this case is coming out to 471 in case of polynomial regression, polynomial EPS regression. Similarly, when I am going with radial, 381 support vectors, and when I am trying out sigmoid, so all the four models I am trying out, I want to see. So in sigmoid there are almost 879, but remember all these are done based on some default parameters. If you see here in case of sigmoid, it has taken epsilon as 0.1, coefficient 0 it has taken as 0, and gamma it has taken. So these are the four assumptions, the default values that are being taken. Now I have an option to keep changing all these values and again look at the goodness of fit of my model. Similarly here also you could see cost, gamma and epsilon are the considerations here. In case of radial I am not looking at coefficient 0. Whereas here in case of a polynomial, cost, degree, gamma, coefficient 0, epsilon, 5 parameters are being looked at. Whereas in case of linear, cost, gamma and epsilon are being considered. So this is how I have to make changes to each one of them so that I can understand the things much more appropriately. And by changing, we have the option of tune.svm as well, depending on how we are changing the parameters of the model. And based on that, we may try out whatever is the best possible parameters that we are getting for each of these models, and based on that we can replace those parameters with our numbers which we have got, and we can go ahead in terms of executing the model again and again. But at the same time, these models itself, I could have gone with a cross validation part. Let's see if there is some kind of betterment. Right, in this itself, even with the default parameters, I could have set the cross validation with the number of elements that are there as a part of my training data. Right, I can very well look at the number of elements that are there as a part of my training data. I can very well set the cross validation 900, and so some different combinations of 937 will be chosen, and based on that the model could be fitted. So one we can do with respect to linear with a cross validation of 937, which can go painful, but still that would give us a slightly improvised kind of a model. But because 937 is too large kind of a stuff, it might take some amount of time in terms of execution. So better we could have reduced it to a slightly lesser set as well. Let's see how much time is it going to take. because once we execute this cross validation, it can actually give us total mean. We'll get two important things when we do this cross validation. We will get, as we have discussed even in classification case, we are going to get total mean squared error. For each of these models, we'll get what is the total mean squared error, and also we'll get the R squared, which is the correlation coefficient squared. So on the training data, of course, these are the things that are there on the training data, but that would be the first point for us to understand where this model is typically heading to. So that's the reason a cross validation can really be helpful for us. So the cross validation is executed for the linear model. Now let me see if I can do the same for the polynomial model. It's better every time we do the cross validation at least. So for the polynomial kernel, so it is executing for the polynomial kernel. Rather than simply doing a very plain basis formula, we can always go with a cross validation with some number. May not be 937, probably you can try a slightly reduced set as well. But yeah, I mean, it's always better to go with different combinations of 937 so that you can understand what is the kind of error that is overall coming up in the model. Right, instead, so your random values really will not have a very significant influence by doing this exercise. So now we are doing the radial kernel as well, and we would also try the sigmoid kernel, and after that we'll try to see what is the output that is coming out in each one of them. And once we have fitted this model, I want to try out testing this model on the test data which is that 401 element, and based on that we need to see what is the level of accuracy that is associated with this model. Okay, and let me also fit the last one, which is the sigmoid kernel. Again, let me remind you, these are all done with the default parameters that are set for each of these kernels, and we have the option to change the parameters for each of the kernels to try to play around with the model and finally create the best possible model, which is giving us the least possible error as well as the highest possible correlation coefficient, both on the training data as well as on your testing data. So that's a kind of an iterative process that I have to leave it to you, because depending on the specific data set that you are working with, the kind of iterations you are going to perform could differ, and in some cases you can very well program all your iterations as well by putting them into loops and see which one has finally given you the best possible outcome out of all the iterations, right? So let it execute the sigmoid kernel as well with respect to the cross validation. Then we'll see what is the level of accuracy that is associated with each of these. So now I am trying to look at a few points out here, right? So I will be taking up the four different models: the linear, the polynomial kernel, the radial kernel and the sigmoid kernel. Now on the training data, I will look at the mean squared error. I would also be looking at the R squared, which will come out as the squared correlation coefficient. Then on the testing data also, again I can very well do the R squared on the testing data. And finally see, for this specific data, if I have to use an epsilon regression based support vector machine, which of these four algorithms is the best enough, going with the default parameter values. So let me just start the process. So fit EPS linear, when I am looking at right here, now when I do a summary, I get slightly better. Now you could see these are the mean squared errors that are coming out in each of the cases for different combinations, because we have tried 937 for different combinations. These are the different kinds of mean squared errors that are coming out. So this is the total mean squared error. So in this case, the total mean squared error is working out to be this much. So I can I'll talk about in terms of million. Total mean squared error is 47.69 million here. 47.69 million in case of linear, and the squared correlation coefficient has come out to 71.57%. This is on the training data. But when I look at it with respect to the polynomial kernel, the scenario is the mean squared error is around 45.28. Looks like slightly reduced when I am working it on the training data, 45.28 million. R squared has worked out to 73.37%, so slightly higher for the polynomial kernel. But when I want to look at it with respect to the radial kernel, things are much better. It's only 25.83 million, which is the mean squared error, with a R squared of 83.11%. So probably on the training data, looks like the radial kernel has done a much better job, where I can also look at even the sigmoid kernel as well before I confirm anything. Sigmoid kernel has gone much worse, where I could see 517 million is the mean. But let me tell you, these are with the default coefficients, default parameters. If I change the parameters, all these could change quite drastically. But here the correlation coefficient is also showing only 9.07. So at least it looks like in this case the radial kernel is doing a good job. But nevertheless, I can very well do my predictions, and from there I can very well look at on the test data which one is doing a better job. So I'll say pred EPS linear. So wherein I'm using the predict function, and fit linear, fit EPS linear is the model, and my test data is the data on which I am fitting it. So I have pred EPS linear. Similarly, I have pred EPS poly, wherein I am using the fit EPS poly model. I am calling the prediction as pred EPS poly. Similarly, I can go ahead with the radial as well as with the sigmoid. Radial, and finally I should look at the sigmoid. So these are the four models that I have used, and I am doing the prediction with respect to these four models as well. So I got my predicted values using all the four models. One, I can go with a plot, right? Probably I would like to show only one of the plots where I can go with a scatter plot. One talking about the actuals. The actuals is coming from test data dollar charges and the predicted is coming from here. So I could try the scatter plot for each one of them in this manner. So probably this is the kind of a scatter plot that is getting created as the actual values are increasing, even the predicted looks increasing. So that's a graphical way that you can very well plan out. But I am more interested in looking at the correlation squared that is existing between these two, which is the R squared on the testing data. So when I am looking at the R squared, which is the correlation squared between the actual data and the predicted data, here it came out to, in linear it worked out to 76.35%, much better. R squared on the testing data for linear came out to be this much. But when I am looking at with the polynomial function, polynomial kernel, the number worked out to 79.22%. So polynomial is doing a slightly better job, but when it comes to the radial kernel, the radial has given me 86.29% accuracy on the testing data. So that is where probably I can rely very heavily on my radial function, right? That's the kind of error that is coming out. 86.29 is the level of accuracy that has come with respect to my radial model, and finally when I am going with sigmoid may not be any kind of an advantage, 16.39%. So going with the EPS regression, I could easily make out that in this case the radial EPS is doing a good job, wherein I am able to get 86.29% R squared on my testing data. So this is what I have explained the whole process, right? It can also use the tune.svm, especially if I want to optimize the parameters of, let's say, gamma, epsilon, nu, etc. cost. I can very well do a tune.svm kind of a function, but of course it will take quite a good amount of time for execution, but that's a kind of an advantage. Otherwise I should try different combinations of gammas, epsilons, all the various parameters, and based on that I should run the model again and again and finally see in which case the R squared is coming out to be much more comfortable, right? So once I have done that, better test it out on the testing data and finally go with the evaluation of the R squared of the model on the testing data to finally say that this model is more and more better compared to the other set of models that we have developed. The same logic I can execute for new regression, right? Everything is the same. I don't want to go through this slide again because everything is exactly the same. The only difference is instead of the type as set as EPS regression there, I am setting it as new regression. So let me create the four models that we have created earlier. I can create all the four models that we have created earlier with the only difference, instead of type being set as EPS regression, now I'll set it as new regression, right? I am calling it as fit new linear as the model. So I am fitting the four different models again to test out. Again, this is a kind of comparison. Again, I'll have a linear model, polynomial kernel, the radial kernel, as well as a sigmoid kernel. And I could also have the mean squared error altogether. I could also look at the R squared from the training data and R squared from the testing data. So this is what we can very well see. Probably we can compare it with respect to the epsilon regression that we have got in the earlier case as well. So let me see how the new regression is working with respect to each of the four kernels. See what is the kind of difference that is working out in in the estimates of each of these models. Okay, now the new linear regression is new linear kernel is taken care of. The same way, probably I can very well work out with the polynomial kernel for the same new regression mechanism. Similarly, we can try the radial kernel as well as, right, I'll also try the radial kernel as well as the sigmoid kernel to typically assess which one is fitting well with the data, and again all these are with the default set of parameters itself. Now, if the cross validation is with a higher set of numbers, then different combinations have to be taken, which is where the process is slowing down very heavily, for which you require more and more powerful servers, powerful computation capabilities of the system, so that all these calculations can be done quite comfortably. As we have seen earlier, different combinations are typically worked out to finally give us the result of the mean squared errors in each of the cases. Right? So that is what will actually improve the goodness of the usage of the model. And that's one of the prime reasons I suggest always while you are building the model, try to put in the cross validation as a part of the model. Right? The cross validation, leave one out cross validation or tenfold. Here I am taking a 937 fold cross validation, which is what is taking a much bigger time frame in terms of building of the model. But in some cases, having an accurate model is much more appropriate than trying to rely on the model errors in the model just because of the random sample that we have picked. So that's one reason why this cross validation can really help us in assessing the goodness of the model quite comfortably. Now let me do the as well, wherein I am bringing in the sigmoid kernel also into picture. Let's see if there is any kind of an improvement each one of them is bringing in over the EPS regression in terms of estimation both on the training data as well as on the testing data. Now looking at these four models, we can quickly look at the summary of each of these models. The linear model, the summary is saying that the total mean squared error is to the extent of 50.49 million. Looks like slightly higher compared to the EPS regression, and even the squared correlation coefficient is working out to 70.89% when we are working with the training data. But when we go ahead slightly in terms of looking at polynomial kernel here, the same logic, but a little bit of reduction again in the mean squared error. 45.96 million is the mean squared error. Even in the earlier case, it was 45.28 in the EPS regression. Here it is 45.96. R squared is working out to 73.44%, going out with the polynomial kernel. Similarly, trying out the radial kernel is more effective. Here also the mean squared error is working out to 27.16 million with an R squared of 83.21%. Probably this is looking more promising. Even here it was 83.11 in EPS regression, whereas in new regression the radial kernel was showing 83.21%. Whereas what happened to your sigmoid? The sigmoid is looking the same pathetic. So it is 359 million in terms of mean squared error, whereas it is 15.61 with respect to the R squared. So these are the numbers on the training data. Now we can very well make the predictions on the testing data, and on the testing data also we can very well compute the R squared to see which one is fitting much appropriate. But again, let me tell you, it is with the default parameters of gamma, nu, epsilon, cos, all these parameters, coefficient 0, all these parameters are the default parameters. So by changing the parameters for different possible values, you might very well improve the performance of the model, and which you should do when you are working with the real world data, right? Now let's try to do the prediction on the test data. I'll call it predNewLinear, wherein I'm using the predict function and the models being fitNewLinear is the model, and I'm using test data. That's how the linear models are being fitted. Then I'm fitting the polynomial model to the data, the test data. So I'm calling predNewPoly. Similarly, I'm fitting the radial model to the test data. And finally, I am also fitting the sigmoid model to the test data. Let's see how the numbers. Again, I could have plotted the scatter plot between the actual and the predicted, but I would prefer going ahead with the R squared. So I'll take test data $charges being the actual values of the charges, and predNewLinear being the predicted value of the charges with the linear model. I'm taking the R squared, the correlation squared between them, resulting in 75.67% on the testing data. Whereas when it comes to the polynomial predictions, it looked like 79.53 is the accuracy on the test data. Whereas when it came to the radial kernel, looks like the numbers are much comfortable. 86.2%. That's the level of accuracy going with the default parameters on the radial kernel, and probably I could also try out the sigmoid kernel giving me a 19.15% accuracy. So overall it looks like the radial kernel going with the default parameters with a new regression giving me 86.2% accuracy, whereas an EPS regression is giving me 86.29% accuracy on the radial kernel. So if I have to choose between these two, I will still choose for the EPS regression itself. So that's how I can very well access the scenario of SVM new regression. The steps are more or less a similar kind of steps. You can quickly go through the steps. Whatever we have done is exactly to the extent of taking care of all these aspects itself. Now moving on to the next, which is the bound constraint support vector machine EPS regression. This is executed through a package kernlab and KSVM function. So let me load the package kernlab. We already know KSVM function, but again for a quick revision of the same, it allows me for different kinds of kernels much higher than what we have looked at in case of the E1071 package. It allows me for RBF dot, polynomial dot, vanilla dot, tanh dot, hyperbolic tangent kernel, Laplace dot, Bessel dot, ANOVA dot. It actually helps me in terms of working with all these kernels. Right now I can look at, again different regressions are there, but I am looking at only the EPS regression. So I am looking at the bound constraint EPS regression, so I'll call it as EPS hyphen VSVR. But I could have very well gone with the other two which we have done earlier, the EPS regression and the new regression, even from this package as well. If I am doing it from this package, I have an advantage that I could have used another 3 more kernels which could have given me the different options in terms of assessing the accuracy of the model. Apart from that, everything else remains to be the same. I have to specify the kernel function. The parameter values, there are again default parameter values that are being considered. You could see here the default is taken as 0.2, cost parameter is taken as 1, epsilon is taken as 0.1. So these are the default values that are being considered. Right, you have to set it to EPS BSVR, and you need to have a continuous response variable Y with the covariates data. All else remaining the same. So I really don't need to really go through the notes out there. I can directly get into the implementation part. Right? So let me call it as fit BSVR linear. I am using KSVM function wherein I am considering charges tilde dot. That's my formula. The data is coming from train data. Then the kernel. Let me go with vanilla dot first. The kernel, I am using the vanilla dot. The type, I have to use it as EPS hyphen BSVR. Right? and parameters I can leave them to be the default. Let me do a 10-fold cross validation rather than 937-fold which I have done earlier, so that the model could be slightly executed quicker. So I'm executing a linear model. Now I can very well go with a polydot to execute a polynomial model. I'll execute all the models with the default parameters. I'll go with a radial kernel, so that the type will be the same. Instead of polydot, I have to showcase rbf dot. Because I am doing a 10-fold cross validation, things are becoming much faster compared to a 937-fold. So that's one performance issue that you need to be aware of. Then if I go with tan h dot, tan h dot, so here also I am calling it as tan h, hyperbolic tangent. Then I could very well go with Laplace dot going with Laplace kernel, going with a Bessel dot representing the Bessel kernel, even if I don't understand the mathematics behind all of them, I can quite comfortably execute them, and a way for me to assess the model is doing a testing on the testing data. I can go with ANOVA dot, and I am using the model as ANOVA, fit BSVR ANOVA. Now we have all these 7 models in front of us. We can very well evaluate the summary of each of these. So again, let me try to form a small table out here. So I have different kinds of kernels to look at. I have a linear kernel, polynomial kernel, radial basis kernel, hyperbolic tangent, which is a sigmoid kernel. Then we also have Laplace kernel, the Bessel kernel, and ANOVA dot kernel. I am looking at the mean squared error in each one of these cases. I am also looking at the R squared on the training data as well as the R squared on the testing data. So look at each of these models again with their default parameters. I am reiterating the stuff with their default parameters. So here for them I should simply type the name of the model. So I could get that the training error is to the extent of 5.7, right? In this, okay, here we are getting the training error which is to the extent of 5.7, right? Here we are not getting the R squared directly. Cross validation error is coming out to 85.17 million. That's the cross validation error that is coming out with respect to the linear kernel function. But whereas when I go with the polynomial kernel, the training error is much lesser, 0.31, and at the same time I could see that the cross validation error also has come down quite drastically to the extent of 47 million. Now similarly, when I am looking at the radial kernel, looks like the error is much lesser, only 26 million is the cross validation error. Training error also has come down quite drastically to the extent of 0.15. So it looks like the radial kernel is more and more appropriate even in this case also. But if I have to look at an H, the cross validation error is too huge. Even the training error is looking too huge. Probably this may not be the choice at all with the default set of parameters. Then if I am going with Laplace kernel, what is the situation? Cross validation error is to the extent of 28 million, more or less in line with your radial, right? Training error is also 0.13, which is slightly lesser than even the radial kernel as well. So something that needs to be looked at with the testing data. And even when I am going with the Bessel, the same thing. It's also on the similar line. 26 million is the training error. Cross validation error and training error is to the extent of 0.16. And even when I am going with the ANOVA, I am getting a similar, I am getting a much bigger result. So probably again it's a choice between Bessel, Laplace and radial. So what we can very well do is we can do the prediction, Pred BSVR linear, where I am doing the predict, the model. The linear model is what is my input, fit BSVR linear, and along with that I am using the test data. So that's how I am getting all my models predicted on the testing data. So I'll use a polynomial function, polynomial kernel, Pred BSVR poly. Similarly, I could very well use the radial for the prediction purpose. So the radial, then we can also use the tan H, which is giving me the hyperbolic tangent prediction. Then I can use the Laplace kernel. Prediction also I can do with Laplace. Bessel, the same lines. And finally the ANOVA. Right, we have 7 different predicted values being created. Now I can look at the R squared between the actual data, which is test data dollar charges. That's the actual data. And predicted data is coming from Pred SVR linear. And I'm taking the squared value of that. So with respect to the linear regression, with respect to the linear regression, the accuracy on the testing data is looking pretty poor, only 48.6%. Whereas when I look at the poly, this is around 76.34% on the testing data. Going ahead with radial, this does 86.46%. So probably radial with bound constraint EPS regression is giving a much better result, 86.46%. Going with tan H, it's around hardly 0.07%, so I can very well ignore the model. And I have to look at the Laplace, giving me 86.27, more or less on the same lines as the radial. And what about the Bessel? Bessel is 85.84, slightly lesser. And finally, going ahead with the ANOVA dot, it is 63 points. So overall, again, it might sound that the radial or even the Laplace, these are the two ones which are giving me a better solution on my testing data when I am applying the bound constraint SVM EPS regression. So that's how I can very well go ahead with the different algorithms. So the kind of options that we have, again, whether it is the SVM package or the SVM function of E1071 package or KSVM function of kernel package, there are so many things for us to customize. One, the parameters, the sigma, the epsilon, the nu, right? Because and even in these parameters, one, there are general parameters like cost, epsilon, nu, etc. And there are kernel specific parameters for each of the kernels, the scale related stuff, the sigma value, the offset value for each of the parameters. Then we have for each of the kernels we have specific parameters which we can alter. The type, depending on the type of the model, I can have EPS regression, new regression, bound constraint EPS regression. So I can change the type, and I can even specify the different kernels. I have an option of 4 kernels under this, I have an option of 7 to 8 kernels under this. So I can change all these things and finally execute all of them on the training data, build models, and whatever the model that gets built, test them out on the testing data, and finally look at what is the level of R squared that is coming out with respect to the testing data, and whichever is coming out with a higher amount of R squared on the testing data could be a better choice for the model building process altogether, provided your testing data is large enough. So this is what I wanted to talk about as a part of this session. So you should be able to use different variants of support vector machines for predicting numerical values as well by having a good understanding of this session. If you have any more further queries, please feel free to get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.